Hello, my dear children. Welcome to the mathematics class. Today we are going to discuss application of derivatives. In this chapter, we are going to discuss the concepts of maxima and minima. Are you ready to listen the class? Right. Now let us discuss the definition of maxima and minimum of a function. See the definition. The maximum of a function is the highest value that it reaches over a closed interval. Okay, my children, the highest value of the function in a closed interval is said to be maximum. Similarly, the minimum of a function is the lowest value that it reaches over a closed interval. Okay, my children, the least value in that interval, in a closed interval, is said to be minimum of the function. Understood these definitions, my dear children? Right. Now come to the first fundamental theorem. Let us see what does the first fundamental theorem say. A function f of x is said to have a local maximum at x is equal to a if f of a is greater than f of x for all x belongs to open interval a minus h comma a plus h, where h is a very small positive arbitrary number. Okay, my children, observe these graphs here. At x is equal to a, this is a graph of the function f of x. This is also graph of another function f of x. At x is equal to a, see here, it has a local maximum in this interval, open interval a minus h comma a plus h. It has a local maximum. Similarly, observe this graph. Here also it has local maximum at this point. Okay, my children. At x is equal to a, it has a local maximum. Understood this point, my children? Note, the local maximum of a function is the largest value only in the neighborhood of point x is equal to a. Understood this concept, my dear children? Local maximum, right. Now come to the next point, local minimum. A function f of x is said to have local minimum at x is equal to a if f of a is less than f of x for all x belongs to open interval a minus h comma a plus h. Okay, my children, understood this point? See this graph. By observing these graphs, you get some idea about local minimum. See here, at x is equal to a, this is the least value, local minimum at here, at this point, at this particular point. Similarly, in this graph, at x is equal to a, see here, this is the local minimum in this neighborhood of a. Neighborhood means very closer numbers to a from left side and from right side. First fundamental theorem is applicable to all the functions continuous, discontinuous, differentiable or non-differentiable at x is equal to a. See here, my dear children, if you observe this graph, this is a continuous function at x is equal to a. F of x is a continuous function, whereas observe this graph, it is not continuous function at x is equal to a, but this fundamental theorem, first fundamental theorem, is applicable for all the functions. They may be continuous or they may be discontinuous. They may be differentiable or they may be non-differentiable at x is equal to a. Okay, my children, understood this concept? Right. Now come to the next concept, that is global maximum or global minimum. What is said to be global maximum and what is said to be global minimum of a function? Global maximum or minimum value of f of x for all x belongs to closed interval a comma b basically refers to the greatest value and least value of f of x over that interval mathematically. Okay, my children, the least value and the greatest values are called said to be global minimum and global maximum respectively. If f of c is greater than or equal to f of x for all x belongs to closed interval a comma b, then f of c is called global maximum or absolute maximum value of f of x. Okay, my children. Similarly, If f of d is less than or equal to f of x for all x belongs to closed interval a comma b, then f of d is called global minimum or absolute minimum value. Understood, my dear children, this concept? Right. For example, consider the graph of the function. See here, a graph of the function is given like this, from here to here, again like this. If you observe this graph, okay, f of x as local maximum at x is equal to c. See here, x is equal to c. At x is equal to c, it has a local maximum, and e also, at e also, and at b also. At all these points is C, E, and B. Okay, my dear children, at these 3 points, F has a local maximum and local minimum at x is equal to A, at x is equal to D, and at x is equal to F. At these 3 points, F has a local minimum. Understood this point, my children, by observing this graph, right? It can also be easily seen that f of b is the greatest value. See here, above all, if we compare the maximum, the largest value here at a b only. So f of b is the greatest value and hence global maximum. This is said to be global maximum or absolute maximum. And similarly, f of b is global minimum. See here, f of d at this point, the least value in that interval a comma b, in this closed interval a comma b. It has 3 local minimum and 3 local maximum points. Out of these local maximum and local minimum values, the greatest value is said to be global maximum, and similarly the least value is said to be global minimum or absolute minimum. Also be careful about the fact that a function has global maximum or global minimum value when it actually achieves these values. Okay, my children, understood this concept? Right. Now observe these graphs, my dear children. Maximum and minimum are in the interior point of interval, closed interval a comma b. See here, x is equal to a and x is equal to b. In this interval, here it has a maximum value at this point. At this point, the function has a minimum value. Understood this graph, my dear children? Local maximum and minimum. Similarly, maximum and minimum are at the endpoints of the interval, closed interval a comma b. See, observe this graph. This is the interval a comma b, closed interval a comma b. This is the graph of the function in the interval a comma b. At these endpoints, it has maximum and minimum values. Understood this graph, my children? Right. Now come to this third diagram, third graph. Maximum and minimum are in the interior point of the interval, closed interval a comma b. At x is equal to at x and y, slope is not 0. Here x and y is not 0. This function is continuous but not differentiable at m comma n. Okay, my children, see here at m comma n. Okay, my children, understood? Right. Similarly, maximum at end point, minimum at interior point of the interval. See here, if you observe this graph, maximum value at the end point. What are the end points here? A and B. These 2 points are endpoints of the closed interval a comma b. So the maximum has maximum at this point a endpoint, but minimum at interval, the interior point of the closed interval a comma b. Understood this point, my dear children? Right. Now observe this graph, my dear children. This is a graph like this. This is a graph of f of x like this. Here, this is a graph of f of x. If we observe this graph, there may be many maximums and minimums, means local maximums, local minimums in an interval. But there will only one maximum and one minimum. It means it has one and only one maximum, global maximum, one and only global minimum, one and only absolute minimum, one and only absolute maximum. Understood this point, my children? See here, at this point f has local minimum. At this point f is said to have local maximum. At this point f is said to have local minimum. At this point f is said to have local maximum. And at this point f is said to have local minimum. At this point f is said to have local maximum. At this point f is said to have local minimum. Understood these points, my children? Right. Out of all these maximum, local maximum, what is the greatest value? This point is the greatest value. So this point is said to be absolute maximum or global maximum. Understood this point, my children? Right. Now come to global minimum or absolute minimum. Out of all these points, see here, this point is said to be global minimum or absolute minimum because this is the least value among these local minimum values. Understood this point, my children? Right. By mistake it is given point of maximum. This is a global minimum or absolute minimum of the function in the interval. Understood this point, my children? Right. For maxima and minima, m, that is dy by dx, tan, the slope of the tangent must be equal to 0. That means dy by dx equal to 0. It must be equal to 0. It means tangent is parallel to x-axis. See here at minimum value or maximum value. At here maximum value, if you draw tangent at the point of maximum, the tangent is parallel to x-axis. At this point of local minimum, the tangent at that point is parallel to x-axis. Similarly, at this point of local maximum, if you draw tangent at that point to the curve, that tangent is parallel to x-axis. Understood this point, my children? Right. Now come to this point of maximum and minimum. So here, if you observe here, it is tangent at this point f dash of x is equal to 0. F dash of x, derivative of the given function is 0. If you observe here, this is increasing this side and this side is decreasing. At this point left side is increasing and right side is decreasing. Means here the sign changes from negative to positive. At this point left side is negative positive and right side is tangent, slope of the tangent is negative. If it changes the negative sign, positive sign to negative sign at a point, then it is said to be point of local maximum. Similarly, if this you see here at this point of minimum, the tangent, if you draw the tangent, see it is decreasing. So slope of the tangent is negative. Here slope of the tangent is positive. If the slope of the tangent changes from negative to positive, then we say that that point is said to be point of local minimum. Understood this point, my children? Right. So by using the first derivative test, we can say maximum and minimum of a function. If at left of at any point dy by dx is positive and right of this point dy by dx is negative, then the point will be point of maximum. See here. Here left side is positive and right side is negative at this point. Then this point is said to be point of maximum. Similarly, on the other hand, if at left side of the point dy by dx is negative, here it is negative, and right of that point dy by dx is positive, here it is positive, then the point will be the point of minimum. Okay, my children, understood this point? Right. Now come to this point. Procedure to find point of maximum and minimum by second derivative test. Okay, my children, this is the second derivative test to find point of maximum and point of minimum. See here, for knowing point of maximum and minimum, first step we have to find first derivative. We have to find dy by dx. Second step, what is second step? Put dy by dx is equal to 0 and find the points for which dy by dx is equal to 0. You know, this is nothing but critical points. Finding the in this step, in this stage, we are going to find critical points, stationary points. In the previous exercise, we have discussed the point. If we solve the equation dy by dx, we get some values for x. That points are said to be critical points or stationary points or turning points. In this stage, we get these points, critical points, stationary points or turning points. Now, calculate d square y by dx square. After that, we have to find d square y by dx square. If for above any value dy by dx is negative, here we got values for x, critical points, stationary points, and turning points. We substitute those values in d square y by dx square. Understood this point, my children? If we get negative, then it will be the point of maximum. If we get negative sign, negative number, then we say that the function is having low point of maximum. If it is positive, then it will point of minimum. If we get a positive number after substituting these critical points in d square by dx square, then we say that f is having the point of minimum. If d square by dx square is equal to 0, in case d square y by dx square is equal to 0, then we have to find d cube y by dx cube and so on. Okay, my children. If d cube y by dx cube is positive or negative, then the point will be neither maximum or minimum. Okay, my children. Right. If d cube y by dx cube is equal to 0, then we find d power 4 y by dx power 4. If it is negative, then it will have point of maximum, and if it is positive, then it will have point of minimum, and so on. Like this we continue that process. But in our study, in our course of study, we stop by this step only. Step point d square y by dx square. After that we get automatically either point of maximum or point of minimum. No need to go further. We don't find d cube y by dx cube or d power 4 by dx to the power of 4. Okay, my children, understood? Right. Now let us take as the graph of the function f of x is equal to 2x minus 1 in this interval 1 comma 2, 1 less than or equal to x less than 2, and f of x is equal to 4 minus x when 2 is less than or equal to x less than or equal to 4. F is here a piecewise defined function. F is said to be a piecewise defined function because in different intervals f of x is defined like this differently. If you draw the graph of this function, we get like this. From 1 to 2 we get like this. From 2 to 4 we get like this. This function has local minimum at x is equal to 1, at x is equal to 1, comma x is equal to 4. Similarly, at x is equal to, it is a monotonically decreasing function and hence neither maximum nor minimum. See here at this point, it is a monotonically decreasing function. Hence, it is neither maximum nor minimum. F of 4 is equal to 0. Here we observe this graph. F of 4 is equal to 0, which the global minimum value, but global maximum value is not defined. Okay, my children. Here, global minimum values out of these local minimum. Here, at the point, local minimum has, and F has a local minimum at this point. Out of these 2 points, which is the least number at x is equal to 4. So, this is said to be global minimum. Okay, my children. And it is not having global maximum value. It is not defined. Okay, my children. The value of the function can be made as close to 3 as we may please. Okay, my children, understood this point? Right. Now let us take another example. Also consider the graph of another function as shown. F of x is equal to 3 minus 2x, 0 less than or equal to x less than 1. F of x is equal to 1, 1 less than or equal to x less than 2. F of x is equal to x minus 1, 2 less than or equal to x less than or equal to 3. So here f is said to be piecewise defined function, because in different intervals it is defined differently. If you draw the graph of this function f of x, we get like this. By observing this graph, at x is equal to 0, it has a local maximum. At x is equal to 3, it has a maximum, local maximum. F has local maximum at x is equal to 0 and 3. And f of 0 is equal to 3. The value 1 over this interval, which is global maximum. Although note that f does not have local minimum at x is equal to 1 comma 2. If you observe this one, at this point, local minimums, we say that it has not having the local minimum. Okay, my children, but it has local maximum at x is equal to 0 and at x is equal to 3. Understood this point, my children? Right. Now see these examples. In each of the following case, identify at if x is equal to a is a point of local maximum, minimum, or neither of them. See, observe this first figure. X to a at x is equal to, say, it has a local maximum. So for in this figure, at x is equal to f of has a local maximum. Now come to the second diagram, second figure. At x is equal to a, it has neither local maximum or local minimum. Okay, my children, we say that it has neither local maximum nor local minimum. Now come to the third figure, this figure. At x is equal to a, it has local minimum. At this point x is equal to a, the function has local minimum. Now come to the fourth diagram, fourth figure. F is not having local maximum, neither local maximum nor minimum. Understood this point, my children? Right. Now come to the second fundamental theorem. Let us see what does the second fundamental theorem say. Following points should be examined for maximum or minimum in an interval. Okay, my children. See, points where f dash of x is equal to 0 means here we have to find critical points or stationary points or turning points. At this case, we have to examine maximum or minimum. And the points where f dash of x does not exist, we have to check. In this case also, if dash of x does not exist, at this point also we have to check maximum and minimum. And at boundary points of interval, if it is a closed interval, at boundary points also we have to check the maximum and the minimum. Okay, my children, understood this point? Right. See these critical points. Come to the next point, critical points. All those points in the interior of an interval where f dash of x is either equal to 0 or does not exist are called critical points. Example, f of x is equal to maximum of sin x, comma, cos x for all x belongs to open interval 0, comma, 2 pi. If you take this example, maximum of the values of sin x and cos x in this interval open interval 0, comma, 2 pi. See here, this is graph like this, Okay, my children. Now f has three critical points. At each points, f has maximum here at x is equal to pi by 4, at x is equal to pi by 2, and at x is equal to 5 pi by 4. In this interval 0, comma, 2 pi, it has f dash of x is equal to 0. Okay, my children, understood? Right. Now come to the next point, my dear children. Test for maxima or minima. Up to now, we have been able to identify exactly which points should be examined for finding the extreme values of a function. Okay, my children. Let us now consider the various tests by which we can separate the critical points into points of local maxima or minima. So, okay, my children, this is the first derivative test. It is the first derivative test. If f dash of x changes sign from negative to positive while passing through x is equal to a from left to right, then x is equal to a is a point of local maximum. Previously we have discussed that point also, first derivative test. If f dash of x changes sign from positive to negative while passing through x is equal to a from left to right, then x is equal to a is the point of local minimum. Okay, my children, this point also we have discussed graphically previously in the previous slides. If f dash of x does not changes its sign about x is equal to a, then x is equal to a is neither a point of maxima nor minima. Okay, my children, if it does not changes its sign, we say that f does not have point of maxima or minima. Note, this test is applicable only for continuous function. This first derivative test is applicable for only continuous functions. If f of x is discontinuous at x is equal to a, then use the first fundamental theorem is advisable for investigating maxima or minima. Okay, my children, this first derivative test is applicable for only continuous functions. If it is not continuous function, we use the first fundamental theorem to test the maxima or minima. Understood this point, my children? It is advisable to apply first fundamental theorem to check the maxima and minima. Okay, my children, understood this point? Right. Now come to these examples, my children. Find the greatest and the least values of f of x is equal to x cube minus 12x, comma x belongs to close interval minus 1 comma 3. Okay, my children. Right. How do you find the maximum and minimum values? First, we have to find the derivative of this f. Then what you get? 3x square minus 12. After that, second step, we have to find the critical points. We have to find the critical points. We get to some critical points. Then we have to substitute that critical point. After that, we have to check. We have to substitute that critical points in f of x, and also these endpoints also. Out of all these points, we can find which is the least number and which is the greatest number. The least number, the least value of f of x is 16. So it is said to be maximum value of f of x, and the greatest value of f of x out of that values is 11. That is said to be maximum value of f. Okay, my children? Right. Now come to the second example. F of x is equal to x by 2 plus 2 by x. Find the local maximum and local minimum of f of x. How do you find? Same steps. We have to find f dash of x. After that, we have to find critical points. Okay, my children? After finding the critical points, we have to find f double dash of x and the f double. In that f double dash of x, we have to substitute that critical points. Okay, my children, here interval is not mentioned, not given. So local maximum is at x is equal to minus 2 and f of minus 2 is equal to minus 2, and local minimum at x is equal to 2, where because f of 2 is equal to 2. These are said to be local maximum, local minimum values. Okay, my children, find the points of local maxima or minimum of f of x is equal to x cube plus x square plus x plus 1. If you find the derivative of this function, you get to x square plus x plus 1. If you try to find the critical points by solving the f dash of x is equal to 0, it is not possible to find the real numbers. We can't find the roots of that equation. So we say that no point of local maxima nor minima. Understood this point, my children? Right. Now come to the second derivative test. If f of x is continuous function in the neighborhood of x is equal to 0, such that f dash of x is equal to 0 and f double dash of a exists, then we can predict maximum or minimum at x is equal to a, not 0. By mistake here also not 0 at x is equal to a by examining the sign of f double dash of a. If f double dash of a greater than 0, then at x is equal to a, x is equal to a is said to be point of local minima. If f double dash of a is less than 0, then x is equal to a is said to be a point of local maxima. If f double dash of a is equal to 0, then second derivative test does not give you conclusive results. Okay, my children. In general, in exercise problems, we use second derivative test. Okay, my children. If we have double dash of a greater than 0, then we say that point of local minima. If we have a double dash of a less than 0, we say that x is equal to a is point of local maxima. Okay, my children. Understood? Right. This is nth derivative test. This is a extension to the previous concept. Let f of x be function such that f dash of a is equal to f double dash of a is equal to f triple dash of a is equal to and so on. F to the power of n minus 1 of a is equal to 0. If all these cases the values are 0 and f to the power of n a is equal to 0, then if n is even, f to the power of n of a greater than 0, it is said to be minima. F to the power of n of a is less than 0, it is said to be maxima. If n is odd, it has neither maxima nor minima at x is equal to a. Okay, my children, we don't go to this nth derivative test. Only we stop by second derivative test. It is only extension concept. Okay, my children, no need to consider this point. Okay, my children, right. Now come to these useful formulae of mensuration to remember. These formulae are very useful to this exercise 6.4. Okay, my children, volume of a cuboid, surface area of a cuboid, volume of a cube, surface area of a cube, volume of a cone, curved surface area of a cone, curved surface of a cylinder, total surface of a cylinder. Remember these points, my children. Note down these formulae in your classwork notes. These are very important, very useful formulae. Okay, my children? Right. See, this is another some more useful formulae. Volume of a sphere, surface area of a sphere, area of a circular sector, volume of a prism, lateral surface of a prism, total surface of a prism, volume of a pyramid, curved surface of a pyramid. Okay, my children, note down all these formulae, mensuration formulae, which are useful. Okay, my children, right. Now come to the definition. Points of inflection. Which points are said to be points of inflection? For continuous function f of x, if f double dash of x naught is equal to 0 or does not exist at points where f dash of x naught exists, and if f double dash of x changes sign when passing through x is equal to x naught, then x naught is called point of inflection. Understood this point, my children? At the point of inflection, the curve changes its concavity. That is, if f double dash of x is less than 0 for x belongs to open interval a comma b, then the curve y is equal to f of x is convex in the open interval a comma b, like this. Similarly, if f double dash of x is greater than 0 for x belongs to open interval a comma b, then the curve y is equal to f of x is concave in the open interval a comma b. If in like this, in this case, the curve will be concave, in the shape of concave. Okay, my dear children, understood? Right. Now these are all the uses of maxima and minima. For marketing purposes, we require vessels of different shapes for which fabrication cost is less, but they could contain more material. Example, 1 liter container of ghee. Okay, my dear children, we have to use in these concepts the concept of maxima and minima practical applications for getting more rectangular land area when total perimeter of land is given. In factories using resources so that the fabrication cost of commodity becomes less. In all these cases, we use the concept of maxima and minima. Understood, my dear children? Right. These are the practical application of maxima, minima. Okay, my dear children? Right. See here, practical application of maxima or minima. In chemistry, we have used the maxima of wave function and radial probability distribution functions to determine where an electron is most likely to be found in any given orbital. In this case, we use the concept of maxima and minima. Similarly, in physics, the maximum or minimum displacement of a wave is known as its amplitude and is occasionally found graphically. We have also solved equations to determine the maximum of velocity and acceleration functions for waves using other physical principles such as the law of conservation of energy. In these cases also we use the concept of maxima and minima. Okay, my children, these are all practical applications of maxima and minima. Right. We use the concept of maxima minima in economics also. In economics, maxima and minima are used to maximize beneficial values, means profit, efficiency, output, etc., and to minimize negative ones, means expenses, efforts, etc. Okay, my children, in the economics also we use the concept of maxima and minima. Similarly, in a metallurgist creates a model that predicts temperature variance with respect to time. The absolute maximum and minimum of this function over any 24-hour period or the forecasted high and low temperatures. In these cases also we use the concept of maxima and minima. Okay, my children, understood? Right. The director of a theme park works with a model of total revenue as a function of admission price. The location of the absolute maximum of this function represents the ideal admission price, that is one that will generate the most revenue. In this case also we use the concept of maximum and minimum. Similarly, a NASA engineer working on the next generation space shuttle studies a function that computes the pressure acting on the shuttle at a given altitude. The absolute maximum of this function represents the pressure that the shuttle must be designed to sustain. In these cases also we use the concept of maxima and minima. Okay, my children, these are all practical applications of maxima, minima in some other areas. Okay, my children, understood? Right.